It's recording now. And then I'll end with a couple of examples which are in production currently. So Ewoks currently is in production at around 10, 12 beamlines at ESRF. Is there an echo online? Somebody asks. No? Okay. Well, I'll just continue until somebody tells me to stop. So what problem did we try to solve? After the upgrade of the ESRF and with the introduction of the new acquisition control system called Bliss, we suddenly got much more requests for online data processing by beamlines. And the beamliners who were doing this in the past, they had their own custom-made systems, either based on workflow management systems or like fully custom tooling, where basically they try to connect tools, scientific tools, which are really designed for offline processing, trying to connect them online to the acquisition, right? So obviously, when going forward into the future, we chose to go for a workflow approach. Not only, because workflows provide inherently a level of abstraction, you decouple basically the description of work from the execution and the visualization. So there's an engineering reasons, but scientists want to hear scientific reasons why you choose workflows. So if a workflow is essentially a recipe of steps to be taken in the data processing pipeline or decisions to be made by an automated acquisition system, so these are the two fields in which we use workflows, then the following properties follow automatically, basically. So the first is reproducibility. So when you have a full recipe, you can always run it again and regenerate your results. You have reusability. Once you have made a workflow, a recipe, you can use that on thousands of data sets to process data. Traceability, so we have data provenance. The workflow itself describes the full history of where data comes from. You can mix both humans and machines. Both of them can create and execute workflows. And finally, you have collaborative data processing. Typically, a workflow, if you think about it, the first step starts typically with like X-ray related data processing. So you need people who are experts in X-ray techniques and beamlines. And towards the end of the workflow, you have, let's say, data processing steps, which are really related to the application in biology or medicine. And workflows allow you to connect those two worlds. So what did we have in mind when trying to think of what type of workflow management system we would use? First, we were just thinking, okay, we choose one and we stick to that. But there's so many different systems around with different features, and you want to actually use the best of all those features, and that's where the meta approach basically started. And also what we wanted to do is to make sure that the efforts we put in could be shared across beamlines and techniques. So nothing beamline specific, nothing technique specific, or even synchrotron specific. Workflows that you create in one system should be executable in the other. Tasks that you implement in one system should be executed in the other. Any changes in workflow techniques in the future in workflow management systems should not affect the users who have been creating workflows for years and developers who have been implementing tasks for years. So that's a very important point. And then the last important point is that it needs to be both lightweight and at scale. With that, I mean that if you want to run a workflow on your PC or laptop, you shouldn't have to install servers and databases and message brokers and all that. You just should run the workflow as if it's a Python script or a command line thing. But when you're at scale, at the beamline or synchrotron, you do want things like monitoring, like what the automated processing is doing, what the workflow is doing, debugging and so on. So you do need databases and message brokers. So Ewoks is not a workflow management system, it's a meta system. It means that we basically decouple workflow definition and task implementation from the workflow management system, which is the execution of the workflow, the visualization, and so on. So Ewoks provides basically two things. You have a convention for defining workflows and implementing workflow tasks. And then you have bindings for the workflow management systems that provide features that we think are useful. So there are literally hundreds of systems out there. That's not an exaggeration. There are hundreds. Some of you may know, I don't know, SnakeMake or Common Workflow Language or Orange. At the designing stage of Ewoks, we made bindings for many systems, more than we needed, just to make sure we weren't biased towards one system or the other. But these are the systems that currently we have in production. So the first system is called Orange. And this one we mainly chose because it has a strong desktop GUI, a Qt GUI. But it has very strong disadvantages. Primarily, you can't run it without the GUI, which is horrible for online data processing, of course. Then you have Dask, which we chose for its parallelization. So it can parallelize tasks using local resources or a cluster. Then we have pypushflow, which comes from the MX community, the molecular crystallography community, because most workflow management systems can only execute DAGs, directional acyclic graphs. But as soon as you have cycles or conditional links to make decision trees, most systems don't handle that. So we have pypushflow for those kind of workflows. And then we have Celery, which is not a workflow management system. It's a job scheduler, which again is basically to make an abstraction for job schedule in general, using either local resources or a cluster. At ESRF, we have a Slurm cluster, but sometimes you want to use your local resources, a computer with some GPU at your beamline. So what does Ewoks provide? A common way to define workflows. We actually use underneath network X, so we didn't even invent that ourselves. And then you need a mapping between that representation, that definition, and the workflow management system, the bindings for those that we support. A common way to implement tasks. So if you're used to something like SnakeMake or the workflow management system, you might not understand because you have a workflow command line tools. But in reality, most things that you run are like Python functions or classes. So you need to have a mapping between the runtime representation of a task, serialization of workflows, for example, to save it in a file or transmit it over the network, again, is provided by network X. Then the only two real things that Ewoks implements, let's say there's a decent amount of code there, is execution events for monitoring. So regardless of what workflow management system you use, there will be events which can be used to either just log or provide some feedback during an acquisition or something like that. And then we have persistency or caching of task results. So I will show a result later on about, it's a diffraction workflow where the first part of the workflow is a calibration. And the second part is processing your data sets. And the calibration part, you also don't want to re-execute that every time you execute the workflow. So therefore you need to cache or persist some of the tasks. As long as their parameters don't change, they will not be re-executed. Also, something we did was add web support because we didn't find a workflow management system that really provided good web support. What does Ewoks not provide? It doesn't provide an execution engine except for a basic serial executor of DAGs. So just executing tasks one by one in a serial manner. As soon as you have loops or conditional links, you can use, for example, pypushflow. It also doesn't provide or handle the data transfer between tasks. That's the work of the execution engine. But you could use the persistency mechanism in the bindings to support that if the workflow management system doesn't really have a good support. What we also don't provide is worker caching. For example, even in diffraction, we use PyPhi. I think the PyPhi developer, the main PyPhi developer, is in the room. The first time you integrate the diffraction pattern, it takes a bit of time, but the next times it's much faster. So the first, there's kind of a process that initializes something and you want to keep that. So also that is not provided by Ewoks itself. It needs to be provided by the workflow management system. And what we also didn't provide is a desktop GUI because this was provided by Orange. So now a little bit of, I was thinking of doing a demo, but I think I don't have the time for that. So I'll just show here the things you have to type. So for the people who are behind the computer, if you have a shell in front of you, feel free to type it out. There's also the documentation, ewoks.readthedocs.io. In the first page, you will see those things. So you can have a look at that and just try it for yourself. So you pip install Ewoks. Then you create a test workflow in JSON and you execute it. So you can try that out for yourself and see how it looks and feels. So that's kind of a command line interface. Then if you want a graphical interface, you can install Ewoks with the orange binding. Execute the workflow, this time with the orange binding, and you will have a graphical interface popping up. And I will show some screenshots, but you can try that for yourself. If you want the same thing, but in the web, you can pip install Ewoks server with the front end. And you will basically see either of these interfaces. So this is the desktop interface. And on the right, you see the web interface. This one is developed by Yanis, which is one of the Ewoks developers. And Orange, of course, already existed. And essentially on the left side or left panel, you have tasks which you can drag on the canvas and you can make links between those tasks and then execute, save and execute and modify workflows. Then the last example, if you want to show a command line interface, I showed a graphical interface. And if you want to just do pure Python, both implement workflow tasks, define workflows and execute workflows, it's all in one slide here. Again, the documentation provides more details, but essentially you derive a class, a task class. In this case, you just add A and B and the result is a sum of those, yeah? And this workflow has two tasks. You connect them together, so you have nodes and links, and you map the result of task 1 to the variable A of task 2, and voila, you have created a workflow. In the workflow, you identify tasks like this. There are other ways than classes. You can have Python functions or scripts or something like that. This is just one example. And then if you want to execute the workflow, you import execute graph from Ewoks, and you execute it like that. If you want to persist tasks, this is one way. I'm not going to go into details. You can look it up in the documentation, but this is just to give you a bit of a flavor how it feels and how it looks. So now to finish, two examples which are in production. The first one is again in the scope of the Streamline project. This is on high throughput power diffraction. So the idea is to build a system that is transportable. So it's not fixed to a specific beamline, it can go anywhere. The users send in sample holders that look like this, and you have powders in each of those holes, except for some holes which contain like a standard or an empty capsule or a hole, which is basically used for calibration. And then the idea of the workflows is that for each sample, so for each of these red ones, you launch a workflow which basically reduces the data, in this case, meaning azimuthal integration of a diffraction pattern. So the workflow looks like this in that case. So you see that these blue guys here, these tasks are part of the calibration. And so only, let's say the red tasks are executed every time you run the workflow. The blue parts are only executed for at the start for the first workflow when you do the calibration. When you do another calibration, of course, they will be executed again. So that's an example of, let's say, kind of data reduction. Then the next example is in the field of spectroscopy. It's not so much for reduction, it's more for online visualization, for the users to know that everything is going well, because they can't really derive that from the raw data. You have to do some processing to really understand whether you collected a good signal. So this was at BM23. So they are using orange, the orange GUI. Basically, this is EXAF processing. So you have the normalized signal here. Then you have a background subtraction, a Fourier transform. You have some statistics and so on. And someone who knows about spectroscopy, from this information, this is running during the scan. So BLIS is basically every X seconds, as much as you want, or as frequent or as not frequent as you want, launches the workflow and the results are being plotted in Flint. This is just one particular example. In this case, also I'm showing here salary, the use of salary, because of course you don't want to execute the workflow in the same process as the acquisition. So that's where you use the distribution, the salary binding. And that's it. So I hope I catch up some time. Thank you.
Thanks for staying in time and for this interesting topic. Are there any questions, comments? Yes. Probably not.
I can hear the moderator, but not the room.
Can you hear the question? No? No?
I can repeat the question.
Okay, so for things like the powder calibration workflow, do you have the ability to, maybe shall I walk over to the microphone? Shall I come over so you don't approve it?
Can the moderator repeat the question? I didn't.
It's probably easier if I walk over here. Can you hear?
Yes.
Yeah, for things like the powder calibration workflow, do you have any sort of workflow steps that can alert you if it goes wrong? Because if you're running this experiment and you run a serium calibration and you reduce that data, you could then say pipe that data into GSAS2 to check that your calibration is refining to a sensible value. But do you have sort of actors that would be able to report to a Slack channel or something like that to say, this calibration has failed, maybe you should come and check the experiment?
Currently not, but if you can tell me how I can, in a reliable way, tell whether a calibration failed or didn't fail, I would be very happy to add that. Yes.
Yeah. No,
but essentially, that has nothing to do with the workflows. I mean, of course, you can, if you have a way of implementing it, it would be easy to add it. Yeah.
So the second question was, the workflows you show tend to be quite sort of on static data. So like an experiment would finish, it would flow into one step into another. Have you implemented anything along the lines of where, say, a detector is streaming data? And if you stream the data into PyPhi, you'll be able to live reduce it. But as soon as you've got one, then you'll be able to fit that pattern before all the rest of the data is reduced. Whereas things like tomography, you might want to wait until the entire data collection is finished before it goes into the next actor. Do these things kind of work out well?
Sure. I mean, the second example actually runs during the scan, right? So the detectors are streaming data, and the workflows are running, right? You can also have a workflow that, uses the stream up until its end, right? So yes, for sure, that's definitely possible.
Cool. That looks great. Thank you.
Okay. Thanks. Thanks, Wout. So if there are additional questions, please address them